Welcome back. We stopped the previous video to allow you time to arrive at the algebraic relationship between the horizontal force acting on a pendulum bob and the variables m, l, horizontal displacement of the pendulum bob, and the vertical displacement of the pendulum bob, delta y. This video will allow you to compare your approach to this problem and your solution to that of the professor. We'll begin where we left off in the last video. There's the same diagram you used that I left you with. And we will follow the strategy suggested in the last video. We will draw the force diagram on the pendulum bob. We will break the tension into the x and y components, apply Newton's second law in the x and y directions, and combine the resulting equations. Let's move our diagram off to the right, and step one, the force diagram. So let's draw in those forces. There's the gravitational force acting downward. The force in the horizontal direction is already shown. There's the tension force acting along the cord of the pendulum. Step two is to break the tension force into its x and y components. So we'll break the tension force into those x and y components now. There's the x component of the tension and the y component of the tension. If you look at that angle phi, it's the same as this angle in here. And if we drew a little triangle here, it would be the same as the angle over there. Applying Newton's law in each direction, we know the acceleration, since it's an equilibrium problem. The acceleration is 0 and the net force is 0, the vector net force, which means the force in both the x and y direction must be 0. So we're breaking our paper into those two columns, and here's the net force in the x direction. And if we look at that, there's I'll say to the right is positive and up is positive. So the force, horizontal force pushing to the right, is equal to or plus the tension force to the left, so that's where the minus sign comes in. Those must be equal to 0 for it to be in equilibrium. And so we have the horizontal force is equal to the magnitude of the tension force in the x direction. Looking at that geometry, if we have this triangle right here, and that angle phi is the same as the little angle here, that's the opposite to it, so it's the sine. So the hypotenuse, the tension, times the sine of the angle phi is equal to the x component of the tension, which is then equal to the horizontal force. Okay, so let's look now at the net forces in the y direction. So there's the tension, the y component of the tension acting upward. Remember, upward is positive, to the right is positive. And then I have to add to that the vector of the gravitational force, which is acting downward. So I write minus mg. So the tension in the y direction is equal to the weight of the pendulum bob. If you look at the diagram again, we can see that's angle phi. This is also angle phi. Ty is adjacent or next to that angle phi, so it's the cosine function. So the tension times the cosine of the angle phi gives us the y component equal to mg. Our goal now is to combine these two equations. So what I'm actually going to do is I'm going to solve this for the tension. So you can see, bringing the cosine of phi underneath here, I have t equals mg over the cosine of theta. And then I would take that expression, mg over the cosine of theta, put that in right here. So we have mg sine theta over cosine theta, mg sine theta over cosine theta. And if you remember, sine theta over cosine theta is the same as tangent theta. So when I solve this for t, mg over cosine theta, taking that expression, putting it in here, I have mg sine theta over cosine theta. Combining that, I'll have the mg sine theta over cosine theta is equivalent to tan theta. So there's our relationship. It isn't quite what we want. It's the force as a function of mass and angle phi, but we want to have mass and length of the pendulum, displacement in the x, and displacement in the y. So we have a little bit more geometry work to do to convert tangent phi into L, delta x, and delta y. So let's move on and do that now. All right, let's look at the geometry of the pendulum. We see that tangent, here's tangent phi equals opposite over adjacent. So this is the adjacent, but notice the L isn't really the adjacent side because the pendulum bob has risen slightly. That's that delta y. So if we take tangent of phi, we see it's opposite. That's your delta x over adjacent, which is L taking away that little delta y. So tangent phi is actually delta x over the parentheses L minus delta y. That would be the length less this rise in distance. With that replacement, we can substitute that in, and we finally have what we were looking for. The force, the horizontal force, is a function of the mass, the horizontal displacement, the length of the pendulum, and the slight vertical rise. And that was our goal for this part of the project. So we'll use that now to try to find actually the number of elementary particles that are on our balloons. We'll continue in a moment.